In this Happy Maths Hour, we're going to talk about tessellation. Now, this man, amazing, Escher, Maurice Cornelius Escher, he was alive for quite a long time during my lifetime, died in 1972, and I just love his artwork. He made mathematically inspired artworks, woodcuts, lithographs, and mezzotints. And probably because I like mathematics, I just love his art. Now, his work explored space in different dimensions, but in particular, the filling of space by regularly repeating patterns, and they're called tessellations. And he was greatly influenced as a young man by the Islamic art that he saw in Spain. Now, here's some pictures. On the bottom right, you see examples of Escher's art. Can you see the reptiles on the bottom right corner? They're crawling out of the page and over the books and back into the page again.
Yeah, it's kind of hard to see it. You have to look really close to see it. But that's exactly what's happening. They're going from 2 dimensions into 3. And they're tessellated on the 2 dimensions, and then they actually coming alive and then going back into the picture again.
It's amazing. I just love that. And that above there, you see Alhambra. What you see is some beautiful artwork. That's what I meant when I talked about Islamic art. And you can see out the windows, you can see the Granada in Spain, but on the inside of that wall, lots and lots of artwork, repeating patterns. And at the top, there are 2 photographs of some of those, not the ones on the wall you see there, but other places in that palace, Alhambra Palace. Now, this is what Escher saw, and he was blown away by it. And he wanted to do his own tessellations, and you see some examples of them there at the bottom. And what we have in this Islamic art is evidence of a very sophisticated culture of the Moors. They were in Spain for several hundred years. They ruled Spain. They built palaces like Alhambra and mosques. Some of those mosques are now Catholic cathedrals. And they didn't decorate them with the human form, only with abstract art. And what we see there shows really quite an advanced knowledge in the 14th century of mathematics, not advanced for their time. Now, this is balls for Spain again. What do you like these balls, Caroline?
I think they are charming. I really like. They're grumpy as anything, but they're cute. In their grumpiness, I think they're amazing. I think it's a brilliant tessellation.
I think this was actually drawn freehand because
I'm sure it was.
If you look at them, they are, each one is slightly different, but they're very, very much, very similar. And I think, let's just imagine that they're all identical and they can fit together, and there are 7 of them. They fit together in what we call a tessellation. And can you imagine putting in more bull's heads, spreading this tessellation out over the whole screen and well beyond? Could you imagine this pattern going on to cover a large wall and going on beyond that? In maths, you can go to infinity and you can imagine these balls going on and on, out into the distance. Now, what do you notice about the orange lines there?
Well, they look like rhombuses. They're parallelograms. They each was it the word similar vertex? Each vertex that maps the same one is touching the balls in the same place.
Yes, and what you see is if you just took what was inside one of those parallelograms and then kept repeating that parallelogram, although there's sort of bits of the ball, not the whole ball in the parallelogram, once you start repeating the parallelogram, you can cover the same space and you'll get the same picture with the parallelograms. You'll get the same picture.
Right. So that you get the same amount of space covered by the parallelograms as by the bulls.
Yes, but the bulls are there inside the parallelograms. It's just that's only bits of bull in each, well, all the bulls there, but he's been cut up and rearranged.
And it doesn't have to be, it's like it doesn't have to be the bulls. It can be, it just goes to show you can make lots of different shapes. As long as they map with the parallelogram, it's going to work.
Yes, and you get the same sort of tessellation if you put flowers in there instead of the bull, or trees, or whatever you like, really. And when we talk about the mathematics of it, we talk about how the pattern repeats itself, not what you see in the pattern, whether it's bulls or flowers or fish or whatever, reptiles or whatever it is.
Yeah.
So now imagine taking this H shape and doing the same sort of thing with that, drawing a tessellation made with the H shape where they all fit together, and you'll get that.
And I can see the rhombuses. Did you use a different shape?
In your mind, did you join the dots?
I joined the dots. I just went straight to the rhombus that you'd had earlier, and I just made some more. In my mind, I joined the dots on the H's.
So now we see not bulls, but H's.
And it's a completely different shape. And yet, it's a similar pattern, what would you call that?
It's a similar tessellation, but is it? Because you could take half the H like that, and you could keep repeating that and fill the same space, or you could take a quarter of the H.
But if you had a stamp that was H shape, all you'd have to do is stamp, 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 stamp. Whereas if you had a stamp that was half an H shape, you'd have to turn it round to stamp the opposite part of the H, or mirror it somehow.
Well, exactly, and that's what Escher did, you see, because when he made his woodcuts, he would have made one bull or one reptile, and then he would have put them into the paint or ink, and then he would have carefully stamped or printed the impression on the paper, and then done it again, fitting exactly as he wanted them to fit into the tessellation. So it was stamp, as you just said, Caroline, exactly. Rather carefully done, but nevertheless exactly as you describe it.
Which was the technology at the time. Yeah, Escher did all of this without a computer.
Well, exactly. And I think most satisfyingly, it was real art, wasn't it?
I have seen some of it in person. Oh, my goodness. And if you want to see it, the best place to see Escher is in Amsterdam.
Absolutely. And when did you ever go to the Escher Museum there, Caroline?
I haven't been to any museums in Amsterdam yet, but next time I go, I certainly will be going to the Escher Museum in Amsterdam.
Well, what you see there is some of the examples of his woodcuts themselves, not just the end result, but the actual pieces of wood that he used to make the prints. And
in the museum. Oh, really? So you actually see the equipment that he used to make the prints.
Exactly. And I think just sort of thinking about how somebody would make this. In fact, you could do it at home. You could cut something out of a potato, okay, and use that and some ink or paint and
I remember doing that in school. I loved cutting out potatoes and stamping with them.
Okay, so that's a cheap and cheerful way of making these same sort of prints, and you could make the pattern using a quarter H like that.
The one on the bottom, if you've got the top right, the one on the bottom left, oh, that is a rotation, but the one on the top left and the one on the bottom right, you actually have to mirror it. You can't just rotate it and stamp it.
No, what have we found in this H pattern? We have found rotations, reflections, and translations.
And translations, which are all the transformations.
And in fact, they didn't exist in the bull. The bull wasn't symmetrical enough. Okay, so indeed, although this pattern looks the same, it isn't the same as the bull pattern in the mathematical sense. Of course, it's not the same in that an H is not a bull, but it's not the same in that it's got more, what we say in mathematics, more symmetries.
And there are only so many types of, what do you call it, structures? What would you call that?
Well, they're called symmetry groups. The tessellations that make the wallpaper patterns are called symmetry groups, and there are only 17.
There's only 17 ways you can cover a wall with repeating patterns. So there's only 17. It doesn't matter what the design is. There are just 17 structures, 17 groups of structures.
Yes, the mathematically different groups of transformations. That's what they are.
I'm going to write that down. Mathematically different group. Woo, that's a mind bender. Mathematically different groups of transformations. Right.
Well, let's look at the bull and the H tessellations. You can see that they both repeat the pattern by a translation in the direction of the arrow, and every single point in the picture gets translated by the same distance in the same direction.
Yeah, that's right. Yeah, it's like all you have to do is follow that arrow and just you move that arrow and you get the next shape. Move that arrow 4 times and you get the next shape.
Well, yes, every point in the picture is moved in the same way.
It's every point. If you move every point, use that arrow to reposition every point in that H, you'll get another H in the right place. Yeah.
Now the H tessellation is based on reflection of a half H. So you get half an H and you reflect it in the dotted line, followed by parallel translations.
Yeah.
Or the H translation can be based on rotations and reflections of a quarter H, followed by parallel translation.
So you'd be rotating and then you'd be reflecting to get that shape down there.
So if you take the smallest piece of the pattern picture and that's repeated, it would actually be the quarter H.
Right. Okay. Okay.
So
you can do this with a quarter H. Okay.
So we've seen something similar about the bull pattern and the H pattern, but actually they're quite different in terms of them, the groups behind them, the groups of transformations.
The H has this one I found very intriguing. The H has a lot more symmetry than the bull.
And yes, so now how could we think about the H, as it were, cut up and fitting into this parallelogram shape? Well, Caroline and I cut this out this afternoon and we tried to do it and we both struggled with it. I found it really difficult.
Toni succeeded before I did. Toni beat me.
But I believed it must happen, but for a while I was wondering if it was at all possible. But it is possible, and there's your solution.
And the reason why I'm going to show off with my camera now. The reason why I failed, not the only reason. I wasn't thinking logically about which edges would actually work if they sat together. But another reason why is because I wasn't cutting it accurately enough. It has to be. I cut up another different one and I ended up literally, I thought, I'll be adventurous. I'll cut this one up in different ways. Well, one of the things I discovered straight away is unless you actually go into the edge and actually cut right through the edge, it's not going to work. The lines, wherever you cut there, it's along there, those lines have to be parallel to each other or it's not going to work. That one doesn't matter so much because that angle matches that angle, so that works wherever you end up. But it really matters. The two things that are critical is that you must cut that edge at the edge, you must cut that one right at the edge. Those were the two really critical things, and that line and that line must be parallel or it is not going to work.
Well, the key thing is that you want your, well, just as we saw that only bits of the ball or bits of more than one ball were in the parallelogram, we're going to put bits of more than one H into this parallelogram.
Yeah, and it really illustrates it beautifully, because you take those bits out and put them back on the H, and you've got that. That's the bit in. Oh, that's not.
And really, it does help your visualization skills to do puzzles like this. I mean, the way I solved it, although I struggled, I have to say at first, was to look at the right angles. And I saw, well, that I had to have a piece that had two right angles and that would fit in the hole at the top, and another piece with two right angles that would fit in the hole at the bottom. Yeah. And those are the two, and they sort of, the one at the top had to come underneath and the one at the bottom had to go on the top. And then I was left with these two triangles. And then I thought, well, yes, well, I've got to put the right angles together. And again, swapping them over, I found that worked. And you can see it in the solution there. So it's, yes, you have to look at the clues in the geometry, look at the right angles. Look at that. I'm not very good at these puzzles, actually. In three-dimensional puzzles, I know that I've solved the puzzle 20 times before, and I still find it difficult the 21st time. Anyway, let's go on. So what question we're answering is, which transformations of a shape are used to make wallpaper patterns? And wallpaper patterns are patterns that cover a flat surface in a tessellation that can extend to infinity, sort of mathematically in your imagination. It can go on forever. And it could be dress fabric, or it could be curtain fabric, or it could be tiling on a wall.
Or upholstery on a chair.
Yes, and you want to be able to seam or join pieces together, strips together, so that your pattern will extend, or however big your surface, your wall, it will go on, and you can keep, repeating the same pattern. So look at patterns now around you and see how the pattern is repeating itself.
And that's a lovely thing to say, Toni. Be aware of patterns in your life. When you're wandering around the street, when you're noticing buildings, when you're in a shop, noticing patterns, and notice what transformations are involved. And you could wonder, oh, I wonder which of the 17 wallpapers this is.
Absolutely. Now, let's think about rotations. So what we saw with the H shape is that we had quarter turns, and with those